Yes, I think you can see the screen.
Yes, sir.
Yeah, good, good. Okay, so let us continue with our discussion. One announcement, this Wednesday we have a test. The syllabus is very small. It's just Hamming code, gray code, BCD code, and then number system binary that you already know. Okay, so these are the only three things. Okay, so let us continue. So we had gone up to the definition of a partial ordered set. So we have defined a relation and a partial order set. It is a set, a PO, a partial order set, sometimes called a poset, is a set with a relation which is asymmetric. Sorry, antisymmetric relation. With a relation which is antisymmetric. Okay, so these are some examples. These are some examples where this is, for example, the left hand side is a power set, the set of all subsets of the set 0, 1, 2, and the inclusion, the set subset relation, inclusion relation is the relation that is defined, is the partial order that is defined. Okay. So similarly on the right you have all the divisors, perfect divisors of the number 36, and you have a relation which is a partial order relation if the one divides the first one divides the second one. Okay, so these diagrams that you see, these are called the Hasse diagrams. These are a nice way of visualizing a partial ordered set. And how these diagrams are drawn as follows. So basically it's an undirected graph. Why? See, usually the relation, the partial order relation should have a direction. If we say A less than equal to B, there is a direction, but we are not keeping an arrow in the edges here. The reason we are, okay, so every node is one of the element of the set A on which the partial order is defined. And the reason we are not having the direction is that the implicit direction is from bottom to top. The implicit direction is from bottom to top. So, we when we draw the diagram, we place the elements in such a way. We place the elements in such a way so that the lower ones are less than equal to the higher ones. Lower ones are partially ordered related to the higher one. Right. So for example, here the null set is a subset of 0, 1, 2. Similarly, 0, 1, 2 is a subset of 0, 1, 0, 2, 1, 2. Similarly, 0, 1, 0, 2, 1, 2 is a subset of 0, 1, 2. So it's ordered that way. So that's the first important criteria, that you have to order the elements of the set from bottom to top in the so that anything in the bottom is not greater than equal to than anything in the top. Not partially ordered relation exists between the one greater than the top. So this ordering is there. One consequence of this ordering is that for the same poset, you can draw the Hasse diagram in multiple possible ways. There are many different possible ways the same poset can be represented as a Hasse diagram. The second criteria is as follows. Just for the sake of neatness, we drop all the transitive relations. We don't draw edges for any of the transitive relations. Right. For example, 0 is a subset of 0, 1, that's fine. But 0 is also a subset of 0, 1, 2, so that we don't draw. So this edge from 0 to 0, 1, 2, that we don't draw. So we just drop the transitive edges. You drop the transitive edges. So you know partial order is transitive, so it's obvious that in all these transitive relations will also hold. So we decided to not clutter the figure any further. Okay, so this is a simple visualization, nothing but a visualization of a poset. It's not a mathematical object. Okay, so we have seen that in any poset, it is easy to visualize using these Hasse diagrams. If you consider any subset, say for example in the right hand side, consider 2, 3, 6, 12, and 18, there are two type of elements which are kind of maximal or minimal. Okay, so there is and again two type of element which are maximum and minimum. The thing you should try to remember between this, which one is which, is that the maximum or the minimum is only one in number, only one, either it is 0 in number or 1 in number, either there is no maximum or there is only one maximum. It cannot have a two maximum. Whereas the maximal or equivalently the minimal, they can be more in number. They can be more in number. Okay. So what is the definition? I'm telling only about the maximal maximum. The corresponding thing for the minimal minimum will also hold. Let me define for maximal and maximum. So maximal is and so we define the maximal or maximum for any subset of a poset. For any subset we can define it. So the maximal is maximal, let's name it capital M. It's an element of the subset such that there is no other element, which is strictly greater than this capital M. There is no other element which is strictly greater than capital M. So 2, 3, 6, 12, 18, you can see 12 and 18 are the maximal elements. There is no element of this 2, 3, 6, 12, 18 which is strictly greater than. Note that it should be strictly greater than 12 and 18. So 12 and 18 are the maximal. Whereas maximum, the thing is, it's also an element of the subset, but every other element of the subset is less than equal to M. Notice the difference. In maximal, we are taking M less than X. Strictly, we are considering the corresponding strict order. We are considering strict order M less than equal to X. Whereas you are in the maximum, we are considering the partial order, X less than equal to M. X less than equal to M. So if you consider the set 2, 3, 6, 18, you should be able to identify one element such that every other element is less than equal to M. So as you can see in this set, there is no such element such that every other element is less than equal to of this subset which is less than equal to M. There is no such element. 12 and 18 are maximal, but they are not maximum because 18 is a member of the subset and it is not less than equal to 12. There is no relation between them. Similarly, 12 is a member of the subset and it's not less than equal to 18 because there is no relation between them. So in this case, there is no maximum. If you consider the set 2, 3, 6, 12, 18, there is no maximum. Whereas if you consider the set 3, 6, 9, 18, 3, 6, 9, 18. So can anybody tell what is the maximum? It's very simple. I'm just still asking. What is the maximum? 3, 6, 9, 18? 18. Because see, look at all the other elements, 3, 6, and 9. 18. Very good. All the other elements, 3, 6, and 9, they are less than equal to 18. Every other element, including that element itself, every other element should be less than equal to the maximum. 18 is also less than equal to 18, so that also holds. Okay, so this difference you note down. So this sometimes may become confusing, but this is this definition will use extensively. So please try to remember this definition. Okay, so let me repeat once again. So maximum means if of a subset means it is that element such that all elements of that subset are less than equal to that element. Everybody is less than equal to that element. Okay. Whereas maximal is that there is no other element which is strictly greater than that element. There is no other element X which is strictly greater than that element in the subset. So these two difference you try to remember. We will use it extensively. All right. Okay, so here is another example of divisors of 60. Is there any other way we can draw the Hasse diagram? I mean, because see the Hasse diagram geometrically, I mean, visualizing, it's just a visualization tool. So one thing I'd like to mention that even though visually multiple Hasse diagrams may look different visually, but they represent the same poset. That's possible. So don't get fooled by that. Maybe they look different, but they still may be the same poset. Okay, so these are the divisors of 60, and that's still a poset. So if we look at the let's try to find out this maximal and maximum. So if we look at the set, let's say 2, 5, 3, 10, 6, 15. So what are the maximal elements? 2, 5, 3, 10, 6, 15. Anybody? What are the maximal elements? 2, 5, 3, 10, 6,
10, 15. 10, 6, and
6,
15.
15. And what is the maximum element?
Sir, does not exist.
Does not exist.
Does not exist.
Very good, very good. It does not exist. Okay, so now that this definition of maximum, minimum is clear, let us try to define two other operations on a poset, two other operations. The first operation is called a meet operation, and the second operation we will call a join operation. So the meet operation is represented by this conjunction symbol. It's sometimes called a cap symbol, x cap y. It's denoted by this x cap y, cap symbol or conjunction symbol. Okay, so if A is a set and less than equal to is a partial order relation defined on the set, you can take any two elements xy in the set. You can take any two element xy in the set, and the meet of xy is an element of that set itself. Okay, so you take any two element, meet of xy, maybe one among them or maybe a third element. It is another element. Okay, so what is the definition? The definition is as follows. You do the following. For x, find out all the w's that are, or rather find out all the w's in A. Let me see. Box. Anyway, I think you can see. Find out all the w elements of A, so that the w is less than x and w is also less than equal to x, and w is also less than equal to y. So this set of all w such that w less than equal to x, w less than equal to y are called the lower bounds of x and y. Lower bounds of x and y. Okay, so let us come to this picture. So suppose you take 12 and 30. 12 and 30. What is the lower bound set of 12 and 30? Note that you have the less than equal to relation.
1, 2, 6, 3.
1, 2, 6, 3. If you take 12 and 30, 1, 2, 6, 3 is, so you leave out 3 and 15. You leave out 3 and 15. Okay. Why you are leaving out 3 and 15? Can you tell why you are leaving out 3 and 15, or should it be left out at all? So 12 and 30, I want to find the lower bound of 12 and 30.
So 3 is included, right?
3 is included. Yeah, so what is the lower bound of 12 and 30?
1, 2, 3, 6.
1, 2
should be GLB.
Huh?
Sir, should 6 be GLB? I'm asking.
6 is the GLB. But I am coming to that. Just a minute. So what is the LB? You tell us what is the LB of 12 and 30. Let us go slow. What is the LB of 12 and 30?
1, 2, 3, 6.
1, 2, 3, 6. 1, 2, 3, 6. Yes, correct. 1, 2, 3, 6. 10 and 15 are excluded. 10, 15, 4 are excluded. Right. 10, 15, 4 are excluded, because if you take 4, it is less than equal to 12, but it is not less than equal to 30. Similarly, 15 is less than equal to 30, but not less than equal to 12. Okay, and similarly, 10 is less than equal to 30, but 10 is not less than equal to 12. No, 10 is less than equal to 12. 10 divides 12. No, 10 doesn't divide 12. Okay, so 10 is not less than equal to 12. Okay, so 1, 2, 5, 3, 6. 1, 2, 5, 3, 6. So this set is the lower bound.
Sir, 1, 2, 3, 6.
Is 1, 2? 1,
5
2?
should not be there. 1, 2, 3, 6. Only.
1, 2, 3, 6.
1, 2, 3, 6. 5 should not be there. Does 5 divide? 5 does not divide 12. 5 does not divide 12. So 1, 2, 3, 6. This rhombus 1, 2, 3, 6. Achha, is 12 and 30 part of lower bound of 12 and 30? Is 12 and 30? Look at the definition. This line you see. W in A, W less than equal to X, W less than equal to Y. So is 12 and 30 part of lower bound of 12 and 30?
No, sir.
Is not,
Yes,
no, because 12 is not, no, 12 is not less than equal to 30. Similarly, 30 is,
Their own lower bounds, they will be apart, means not in common.
no, but they should be, a W should be less than equal to both X and Y.
Okay, okay.
Both X and Y. See, that's why I talked about this. That you have to think. It should be the lower bound of both. It should be a lower bound of both X and Y. Okay. And then you take the maximum of all this lower bound set. Maximum of this lower, not maximum of this lower bound set. So 1, 2.
Then, sir, is 12 belonging to the lower bound or 12 also not?
No, because 12 does not divide 30.
Okay,
I am
yes.
finding the lower bound of 12 and 30. 12 doesn't divide 30, so 12 is not less than equal to 30.
Okay, sir.
So both 12, any member of the lower bound will divide both. So what is the common name? If we take this division case, what is the common name of 12 and 30? What is the common name of 12 and 30? Common name we use in arithmetic for this relation, divide by relation, divisor relation. These all the divisors of both 12 and common divisors of 12 and 30. These are 1, 2, 3, 6. These are the common divisors of 12 and 30. Okay, these are the common divisors of 12 and 30.
Okay.
Sir. So now the maximum among these common dividers, we call it the GLB, the greatest lower bound, the maximum element of the lower bound set. So 1, 2, 3, 6. What is the maximum element? What is the 6 is the maximum. So I think if you talk about this divisor relation, it is the greatest common divisor. It's the greatest common divisor of 12 and 30.
Yeah, I can just come in. Just one thing I wanted to say. That is, in the lower bound set, if you want to, I mean, for the maximum to exist, all the elements should be comparable among themselves. Otherwise, you can't define the maximum, or for that matter, the minimum, when you consider the upper bound. Yeah.
So let us take an example. For example, consider the element X is 20 and Y is 12. What is the lower bound set of 12 and 20? What is the lower bound set of 12 and 20? Anybody?
4, 2, 1.
1, 2, 4.
1, 2, 4. 1, 2, 4. 1, 2, 4. Yes, 1, 2, 4. What is the greatest common divisor? Sorry. GLB. What is the GLB? 4. 4 is the GLB. Okay. All right. So now let us look at the joint definition. So it's denoted by this lower this cup relation. It's X, the disjunction relation. If you look at logical operations. Okay. So just as you define the LB set, you can define the UB set, the upper bound set. Okay. So this upper bound set are all elements Z of A, such that x is less than z as well as y is less than z. X is less than z as well as y is less than z. That set we call as the UB set. So for example, please.
Yes, sir. So can you give an example where it's not compatible? I mean, anyway, one will be there. So can you just give an example? I didn't get that point.
An example of? Repeat again.
Not compatible.
Not comparable.
Compatible.
No, we are. So what we mean is that see, if you take the entire lower bound set, so every element of the lower bound set should be connected to every other element. Note that you might ask why this 1, 2, 3, 6, why everybody is connected to, okay, here everybody is connected to this. See, the thing is that we are not drawing the transitive relations. We are not drawing the transitive relations. Okay, so transitive relations exist, but transitive relations you can follow a path to get a transitive relation from, you have to go from bottom to top. So what we mean to say that every two elements should be comparable. Okay, for the maxima two in any set, forget about the lower bound set. Any set they should be comparable. Otherwise, there is no maximum. For example, 12 and 30 are not comparable. So you cannot find a maxima in a set 1, 2, 3, 6, 12, 30. You cannot find a maxima. You can only find a maximal element because 12 and 30 is not comparable.
But sir, like we can find a 6.
Okay, so let me restate the definition of comparable here. X and y is comparable if either x divides y or y divides x. So do you think 12 and 30 are comparable?
No, according to that definition, it isn't, but we can get a GLB for 12 and 30, right?
Yeah, so we are looking at the, yes, exactly. But see, the GLB is the maximum of the lower bound. So what is the lower bound set of 12 and 30? Lower bound set is 1, 2, 3, 6. 1, 2, 3, 6. Okay, so in this set 1, 2, 3, 6, you take any two pair of element, either the first one divides the second or the second one divides the first. 1, 2, 3, 6. You take any pair of elements. So 1 and 2, 1 divides 2. 1 and 3, 1 divides 3. 3 and 6, 3 divides 6. Okay. Oh, no. So CRM, what do you mean by that? Every pair of elements are comparable?
Yeah, so if you take the set of lower bounds, you should be able to define the minimum. No, you want to define the maximum. Yeah, you want to define the maximum. So as you are taking this, say between 12 and 30 in that thing, so the
set lower bound set is 1, 2, 3, 6.
Yeah, so 1, 2, 3, 6. So all pairs are comparable, and among them 6 is the maximum. Because if a pair is
definition of comparable, what is the definition of comparable?
Yeah, comparable means you can decide whether A is less than or equal to B or whether B is less than or equal to A. You can compare them.
Okay, but here 2 and 3 are they comparable?
No. See, over here, what is happening is okay, between 2 and 3, okay, they are not comparable, but you have, yeah, so okay, so I think there yeah, so all of them, 2 and 3, they have, I mean, you have an element 6, yeah, okay, so maybe that is not exactly correct. So for all elements, you'll have to have you'll have
maximum exists. I think.
Yeah. The maximum must exist in that set. Yeah, that's right.
Maximum one exists. Huh.
Yeah.
Comparable. That's a different.
Yeah. So it is
in the next situation we'll have it. In the next definition we'll have it. Huh. Here it is not necessary. Yeah. It has just a maximum has to exist. That's it.
Yeah, that's it. Yeah.
Does that answer your question? You are
yes,
asking.
Sir. Thank you, sir. Yes, sir.
Okay, so similarly, you can define an upper bound. Upper bound of two element x and y are the subset, are the elements that are greater than equal to both x and y. And the smallest among them, the minimum, not smallest, the minimum among them is the lowest upper bound. So if you take 10 and 6, if you take 10 and 6, what are the upper bound set of 10 and 6? If you take 10 and 6, what is the upper bound set of 10 and 6?
12, 20.
30 and 60.
12, 30 and 60. And what is the lowest upper bound?
12 is not included, right?
No, only 30 and
Sir,
60.
only 30 and 60. Right?
Only 30
30
and
and
60.
60. Yeah. 12 is not included. 12 and is not included. Yes, it has to be both 10 and 6. It has to be greater than equal to both 10 and 6. Okay, so what is the minimum upper bound?
30.
Why 30 is a minimum upper bound? It has to be the minimum, not the minimal. Minimum. So 10 and 6.
Yeah, it is the minimum.
It is the minimum. No, sorry, I missed it. So 10 and 6. What is the upper bound set? 10. We are talking about 10 and 6. What is the upper bound set?
30 and 60.
30 and 60. Yeah, and the minimum upper bound is 30. Good. Minimum upper bound is 30. You can check any two. For example, if you take 2 and 5, if you take 2 and 5, what is the upper bound set? 2 and 5.
20, 30, 60.
30.
10, 20, 30, 60.
10,
10,
20,
20,
30,
30, 60.
30, 60. And the minimum lower bound is 10. Minimum lower bound is 10. Right. So then that is the join of. Okay. So if we talk about this divisor relation, what is 10 actually? What name we call it usually? 10 for 2 and 5. It's the least common. Yeah, it's the least common multiple. Okay. So that's so basically now we have defined two operations, meet and join, and these are very critical operations, meet and join. And for every two element x and y, we have defined how you can find its meet and how it can find its join. All right. So now there are some posets whose structures are very nice. Some posets whose structure are very nice in the sense that you take any two element x and y in that poset, there exists a meet and there exists a join. They have both a meet and join for every pair of element. So if it is such a nice structure, if the poset has such a nice structure that you take any two element, you can find out a meet, you can find out a join. If that be so, such a poset would be called a lattice. Would be called a lattice. Okay, so it's a lattice. So let us see. There are some nice structures
Sir?
that will. Please.
Sir, you did not say that for every pair of x and y there should be a meet and a join. They can or they cannot have us. Is it like that?
If they exist, then that poset would be called a lattice.
So they cannot. There is also
If
there
you
might
find
be
out-
cases where do
Yes,
not exist.
if you find out two elements x and y which do not have either a meet or a join or do not have both, then it is not a lattice.
Yeah, so a poset did not be a lattice. For example, your say a binary tree structure. So that is an example of a poset, but not a lattice.
The parent-child relation, if you see, if you take a binary tree, it's a poset but not a lattice. Let us look at these examples. Let us look at this example. The left-hand side, this chain, is it a lattice?
Yes, sir.
Yeah, you take any two element. For example, take the lowermost and the topmost. What is the meet of lowermost and topmost?
Lowermost.
Lowermost. And if you take the what is the join of lowermost and topmost?
Top.
The topmost. You take the lowermost and the second element. What is the meet? What is the join?
Sir, meet is the lower one and the
second one.
top. Join is the top. Middle one.
Middle one. Join is the middle. So one thing to be okay. So suppose this was a chain containing 4 elements. If you take the middle two, what is the meet? What is the join? If you take any or any two, say suppose this is a k element chain. It's a k element chain. You take any two elements which are neither the beginning or the end of the chain. So what are the meet and the join for them?
Sir, in this case, meet should be the always should be the lower one, and the
Lower
join
one.
always should be the upper one.
Exactly. So for a chain, these two are very simple. For a chain, the meet and join is very simple to decide. Okay, for this structure, the second structure, this rhombus kind of structure.
So any chain is a lattice.
Any chain is a lattice, exactly. So you take any chain, you can close your eyes and say it's a lattice, always a lattice. So if you take this structure, this rhombus kind of structure, is it a lattice?
Yes, sir.
Yes, sir.
It is a lattice. Okay. One thing also you observe that you can think of this as two chains, the left chain and the right chain. You can think of this as two chains, right? So so each of the chain is a lattice. So this will also be a. In fact, this will be a lattice, and also see. Okay. Okay. I mean that's a thumb rule I'm saying, but go by the definition. Third one, is it a lattice?
So it's combination of three chains, so it is a lattice.
No. Sorry, I'll come to that later. But according to the definition of lattice, does every pair of point have a meet and a join? Does every pair of point have a meet and a join? Yes, every pair of point has a meet and a join. See, how can it not have a? How can it have a meet and a join? You see. So you take 2 points, if you can connect them by a chain, of course there is a meet and a join. You take any 2 points and you have a chain connecting them, you of course have a meet and a join, because a chain always has a meet and a join. Right, so that is possible. So here you take any 2 points, you can always connect them by a, okay, beyond that also they can have a meet and a join. If they are not part of a chain, you should see that if these 2 chains intersect somewhere, this chain and this chain, does it intersect? Okay, then also it will be a lattice. If they intersect at 2 points, they will be a lattice. So, and anyway, by definition, this is a third one is a lattice.
Yes, this one has a name also. It's called a diamond lattice.
It's called a diamond lattice. Yes, it's called a diamond lattice. What about the? I think fourth one is easy. You can extend similar logic to tell the fourth one is also a lattice. Fifth one, is it a lattice?
Yes, sir.
Yes, sir.
Okay, so if you take this point, I don't know if you can see this point and this point. Do they have a meet and a join? Every pair of point, do they have a meet and a join?
Yes, sir.
Yes, every pair of point have a meet and a join. What about the sixth one? Does every pair of point have a meet and a join?
Sir, not lattice.
The sixth one is not lattice. Which pair does not have a meet or a join?
Sir, the upper half 2 points.
Upper half 2 points. So this point and this point. Okay. So why they do not have a maximum or a minimum among the lower upper bound or the lower bound and the upper bound?
Sir, they do not have a meet because the candidates are the lower half and they do not have a
right. So these two are maximal elements of the lower bound set. This and this are the maximal elements. These are the maximal elements. Right. Similarly, if you look at these two again are the max. There is no maximum element. These two are maximal elements of the lower bound. Okay. So I think one thing you are already noticing, that moment we are losing planarity, it may not be a lattice. Okay, so you see these two are intersecting here. These two are intersecting.
Sir, what do you mean by planarity?
Oh, planarity means you can have a path. You can draw it on a plane without intersecting edges.
This one is planar.
Oh, this one is planar?
Yeah.
Oh,
of
yeah,
course.
yeah. This one is planar. Sorry. Okay, but one thing you see, what is anyway, let us not go into that. There is a pattern that if there are intersecting relations, intersecting edges, you
No, I think it is better not to go
better
that
not
way.
to go into that pattern. Yes, okay.
Because you can draw it without intersecting edges also.
Yeah, this you can draw without intersecting edges. This you can draw without intersecting edges, right? Yes, this is planar actually. But there is a relation between planarity of lattices. There is a theorem on planarity of lattices. We will go into that later. Okay, what about this? The 1, 2, 3, 4, 7th one?
Not a poset, not a lattice.
Not a lattice. Why not a lattice? Which two elements are not having a minimal set?
So the upper two.
Upper two. What about this middle one and this one? Do they have a join and a meet?
Sir, which one, sir? Can you please once
Yeah,
again refer?
this middle one. So the second, if you go from the bottom, the second highest element.
Okay,
Not
and
second highest, the
the other
second lowest. Yeah. This and the other
and
one
the
is
other element?
any of this one immediately above that. Do they have a meet?
No, sir.
They do not have a
No,
meet.
sir.
Do they have a join?
Sir, why they don't have meet? I can't understand.
Yeah.
sir.
So what is the lower bound set of this one and this one? This one and this one. What is the lower bound set of this one and this one? You go from the bottom, the second level, and the third level, anyone from the third level. Do they have what is the lower bound set?
So we cannot go reverse, like in the reverse direction. Or
No, but there will always be a lower
Okay.
bound set, no?
yes, sir. Yes, sir. That is not a low. Means it does not have any lower bound.
It does not have any. No.
Sir, can you mark the vertices by 1, 2,
Wait,
3, 4? That's confusing.
wait. Let me see how I can do that. Just a minute. I'm trying to find the pointer.
It's better if you open it in external.
If I open in external, okay, yeah. I don't have external. Wait, or maybe let me number them. You try to know the numbers. So the bottommost one, let's name as 1. The next one as 2. Then 3, 4, 5. You go from bottom to top. Keep on numbering them, and left one has higher priority than right one. So 1, 2, 3, 4, 5. So I am talking about 2 and 4. What is the lower bound set of 2 and 4?
So 2.
It's just 2. And what is the maximum of this lower bound set?
2.
2. So meet exists. What about 2 and 4? What about join? What is the upper bound
4,
set
5.
of 4, 5? And what is the minimum?
4.
Minimum is 4.
Sir, I think between 3 and 4 there won't be any meet.
Exactly. Between
It's between 3 and 4 and between 1 and 2.
Between 3 and 4 and 1 and 2. Between 3 and 4 and 1 and 2, there is no meet. There is no meet. There is a join. What is the join between 3 and 4?
5.
What is the meet of 3 and 4? Doesn't exist.
Yes.
What is the meet of 1 and 2?
So it doesn't exist.
Doesn't exist. What is the join of 1 and 2?
3.
3. Okay. So 1 and 2 doesn't have a meet.
So 1 and 2 join is 3. But so 3 and 4 both are there, so it should not exist.
Oh, right.
Yeah, it should not exist. Right. Okay. Okay. So, but see, let us draw this additional relation between 1 and 2.
Excuse me, sir.
Yeah.
So why 3 and 4 doesn't have a meet?
Okay. What is the upper lower bound set of 3 and 4?
So 1 and 2.
1 and 2. And what is the maximum among 1 and 2?
2.
Maximum and 1 and 2 is 2. Why 1 and 2 is 2 maximum?
Okay, so okay.
Just a minute. CRM is calling. Let me take. Hello.
Hey, if you want to update the slides.
Oh, okay. I'll do that. Just a minute.
Okay.
Wait. I'll just hold on a minute. I'll. I'll share a slightly corrected slide. You just give me a minute. Okay, so we'll go by this slide later. Anyway, okay. All right. What about the last one? Achha, between the last but one and so this one and this one, we have added a relation between 1 and 2. So does it make it a lattice? Between 1 and 2, we have added an. Does it make it a lattice?
Yes, sir.
So one thing you notice that you take any 2 points and you try to see a path from the one point to the other point. You try to find first of all, you try to find a path from one point to the other point. And if the path always goes down or always goes up, it cannot go up, come down, and again go up. Then it's a lattice. So here, it is not a lattice because, no, here it is true. If you have to come down and go up, then it is not a lattice. You take any 2 points, you try to find a path between them. And if the path always goes up or always goes down monotonically.
Sir, but in the fifth image, it's also not true, right?
In the fifth image, wait, in the fifth image.
The upper half 2 paths, the 2 points, we can't have a path that can only go up or only go down, but it's still a lattice.
It is still a lattice. Okay. So I'm wrong. I'll check up. I just missed this. Yeah, there's a rule. I'll tell it that in the next. I have missed it. I'm forgetting it. Okay, let us look at the last one. Is it a lattice? Last one. Last Hasse diagram. Is it
yes,
a lattice?
Sir.
It is a
Yes,
lattice.
sir.
You take any 2 point, you can find a least upper bound and a greatest lower bound. You can find a meet and a join. Right?
Yes,
you can find
that's called a pentagon lattice. Okay.
Yeah, it's called a pentagon lattice.
Sir, what is the problem with fifth one?
No, I maybe I said wrong. What I said is that if you take any 2 point, you can find it out yourself. I'll also find it out myself. So if you take any 2 point and if you connect them by a path, the path will always go up or always go down. It cannot go up and come down. If that is so, then it is a lattice. But maybe I'm wrong. I'll read up. I'll read up and tell you. You can also read up yourself.
What is the thing?
There is a rule. I'm not entirely correct. I'm not entirely sure I am correct. The thing is that you take any 2 point and you try to find a path between them. And if the path monotonically goes up or monotonically goes down, then it's a lattice.
You can just check on this the diagram, which is 1, 2, 3, 4, 5, 6. You can check whether it works on the sixth item.
Yeah, maybe the sixth one is a lattice. No, it's
no, it is not a lattice.
It is not a lattice. No, it holds, but that should go for any 2 points. Any 2 points. Any 2 points. Yeah, it doesn't hold. See the top two, the second level from the top. These two you have to go down and come up.
Yes, sir, but in the left one also,
In the fifth one also, we have to
and
go
the
down
fourth
and
one
then come
also.
up.
It's
Fifth one also. You have, yeah. Maybe I'm wrong. Yeah, that's right. That's correct. Maybe you can look up. Why don't you look up? Yeah.
So that is being violated, as you can see.
It is violated. I'll find out. I'm making a mistake. I'll find that out. Okay, so these are some examples. But what I would suggest is that I'm talking about all these chains and all these things. But I think you try to follow. Deduce from the definition that for any 2 points, if you can find a violation, that means there is not a meet or a join or neither, then it's not a lattice. You try to look for these violations. Yeah.
Sir, so in the given diagram, the fifth and the sixth are not lattice.
Fifth and the sixth are not lattice.
The fifth one is a lattice. Sixth one is not a lattice.
Sixth one is a lattice. You cannot find a pair of point. Any pair of point has a meet and a join.
No, sir.
Can you give an example of a pair of point in the sixth one, which does not have a meet or a join?
Sixth and seventh are not lattices.
Oh, sixth and seventh. Fifth and seventh.
Sixth and seventh, those are not lattices.
Fifth is a lattice.
Yeah, fifth is a lattice.
So fifth is a lattice, but sixth is not.
Sir, how is the eighth one a lattice?
Can you give me an example of a pair of point which does not have a meet or a join?
Sir, yes, the last level and the second last level, they have two maximums.
Which 2 points? So let us clockwise.
The lowermost point and the middle point, sir.
Lowermost point and the middle point.
Yes.
The last one, the pentagon you are
Sir,
saying.
second last. Pentagon.
Oh, second last.
Yes.
Top one and rest.
No, sir, lower one, lowest, and the second last. Yes, sir.
What is the what is the meet of these two?
Sir, join, sir. It has two joints.
No, why you take this?
Oh, sorry, sir. Maximum means it has two maximums.
No, you take that point itself. You are talking about the vertical segment.
Okay. Yes,
that's
sir.
the chain.
It
no?
could be that point also.
Yeah.
Excuse me, sir.
Yes, sir.
Yeah.
Sir, in the fifth one, if we take the second topmost 2 points.
Okay.
And if we calculate the meet, there are 2 meets, so we can't find the greatest one.
There are 2 meets. Why there are 2 meets? What is the lower bound set of these two? What is the lower bound set?
Sir, if we number it from bottommost 1, 2, 3, 4, 5. So the lower bound set will be 1, 2, 3.
No. It will be only 1 and 2. 3 is not a lower bound set, part of the lower bound set. Because lower bound set has to be lower than both 3 and 4, both 4 and 5.
Yes, sir. So 3 is lower than both.
No, both it has to be, and condition. 3 is lower than 4, but it is not lower than 5.
Okay.
It's lower than 4, but it's not comparable to 5. It's not lower than 5. So only 1 and 2. Only 1 and 2 is the lower bound set, and 2 is the maximum among that.
Sir, can you explain the structure of the poset of pentagon? Means which is the lower level, which is the upper level? Means I am confused in that.
Okay. So first of all, you tell me, is it consistent? No, consistent. You cannot talk about this. So easy Gallic acid diagram.
Not so difficult. See this. Why can't you make out the lowest and the highest one?
You just go from bottom and go to the top. Scan from the bottom to top.
Okay, sir.
You scan from the bottom to top, and that's the order.
Means lower height means lower element, right? That is the thing.
Yeah, each one is at a distinct level.
Maybe yeah. If it was a blackboard, it would have been clear. But anyway, here maybe because of the small screen, it's difficult to figure out.
No, every element is at a distinct level.
Every element is at a distinct level, exactly.
Okay, sir.
Okay. Okay, so I'll quickly state some lattice properties.
I think we
are out of time.
Yeah, we have completed. Better to do it in the next class.
Okay. We'll do it in the next.
So next Wednesday there is a test that has been announced.
So next or this one?
Next Wednesday means
day after tomorrow.
Day after tomorrow.
Okay.
8 o'clock in WBCM. You log into WBCM, you will get your question paper, and then you have to submit in WBCM only. Okay.
Sir, handwritten or typed?
Handwritten.
This one you'll have to. The questions have been designed so that you can. You can work out by hand, but you'll have to type in a plain text file.
Oh, you can type in a plain text. Yes. Yeah. The answers actually can be typed in plain text.
Sir, it is a choice, right?
WBCM, right?
So, sir, is it mandatory to write? Type only.
Yeah. You can work out on paper, but you'll have to type the answers in a plain text file and so on.
See, the answer will be very small. Just one line you have to type.
Maybe a few lines, but
maybe a few lines. Yes.
Not very big.
We are not asking for the procedure. We don't. You need to upload how we have got the answers. We just want the answers, nothing else. Okay, and the answers are just one or two line.
Sir, what if we need to write some mathematical symbols? Then
whatever you.
No need. The answers will not require any mathematical symbols.
Sir, what about the extension? Just plain text means just .txt.
Yeah, txt file. That's all.
Okay, thank you, sir.
We can give you a provision to upload your working, but that will not be a critical submission. So these answers you'll have to submit within the time. The working you can submit maybe within a little bit of extra time. Yeah. Okay.
And sir, the MD5 checksum as usual.
Sorry?
The MD5 sum.
So, yeah. That is for the recording. So please have a setup so that your face and hands can be recorded, and then you're supposed to keep the recording with you, and you got to send the MD5 sum of the recording. Yeah, upload the MD5 sum of the recording.
Okay. And today we are meeting at 2:30 for the lab assignment. We are meeting at 2:30. We'll briefly meet. We have already taught it in theory, so we'll briefly meet and we'll decide on that. Okay.
All right then.
Okay. Bye.
And sir, the test will start at 8 itself, right?
8. Sharp at 8.
And end at 10.
End at 10. 2 hours.